Hi, welcome to es301 Engineering Analysis. This is chapter 18 on interpolation. So here are the learning goals. At the end of this, you'll understand how to implement Newton's divided difference method for various powers of interpolation. You'll know how to estimate the error in Newton's divided difference method. You'll know how Lagrange interpolating polynomials can also be used for interpolation. You'll be able to implement inverse interpolation using the Lagrange method. You'll recognize how spline interpolation works, and you'll know how to do multidimensional, or in our case, it'll be bilinear interpolation. All right, so first I just want to mention what is interpolation. Interpolation very simply says, given a couple values, for example, the one I have over here on the left and the right, I want to estimate some value, maybe in the middle here. I want to know what is the function value at that point, right? And so if I just had these 2 points, most common type of interpolation might be what would be called a linear interpolation. Just put a line through there, and I would say my value is going to be that point there. Now, clearly, if I had more points to go ahead and use, I might get a better estimate. So if I added this third point here, now I'd realize, oh, I bet this function has some sort of curvature to it. Maybe it's something like this. And so I would be much better off estimating my value up there at a larger value. If I had this fourth point, now you realize, oh, I've really got some sort of more curvature going on. It probably looks something more like this. And so now I'm going to have a new estimate of what my value is. So clearly, the more points that I have, the better my estimate is going to be. Obviously, clearly also, the closer they are together. But what we'll notice is that usually functions have some sort of curvature to it. And so I don't necessarily always want to do a linear interpolation. I might want to put some type of curve in there. And we're going to look at various methods to do that. We're going to be looking at Newton's methods, Lagrange polynomials, and then we'll also be looking at spline interpolation. They're all just 3 different techniques that accomplish a very similar thing. All right. So first, we're just kind of talking in general what we're doing in all these methods is that we're going to go ahead and find some function f that is going to be some polynomial, often nonlinear polynomial, and we're going to go ahead and fit that between all of these points here. And the other thing to point out is that I can exactly fit all of these points if the order of my polynomial is the same as the number of points that I have. But often, if I have, say, 100 points, I'm not going to want to fit a 100-order polynomial to it. So usually I'll fit a lower-order polynomial, maybe a second or third-order polynomial for all the points that I have. Let's look at a pretty low example. The very simplest polynomial I could do would just be a0 plus a1x, which would be what is called the linear interpolation. And you're probably familiar with this. This is just drawing straight lines in between all of those and estimating my value at each of those values. So here's the function. What I'd be doing is, for example, this right over here is f1 of x, and there's going to be a function for each one of these segments that I have. This is my linear interpolation method, and this first point is x0, the next point is x1, and this right over here is just essentially df dx. And so I'm going to go ahead and multiply df dx by delta x, how far along this line that I am. So there's the most simple type of interpolation, but it isn't particularly accurate. Often there's some sort of curvature to the functions, and we'd like to go to get a better way to do it. So we're going to look at some various methods to do that. So first we're going to look at what's called Newton's divided difference method, and I'm just going to look at it in the most general case. Okay? So here's kind of what we're going to be doing. Again, we've got some sort of function that we're going to be interpolating between our points, call it f sub n. And when we'll use Newton's divided difference, we're going to write our polynomial in a slightly different form. And this is the form we have here. I'm using b's instead of a's because they're going to have a little different constant values. I have b naught, and then b1, x minus x naught, and then b2, and I have these series of x minus x0, x minus x1 multiplied. And as I get really high orders, I have more and more terms. Now, clearly this has the same general function or similar value as a naught plus a1x plus a2x squared, etc. If I was to multiply this out, I could determine what my relationship are between b naught and a naught. They're just going to be constant values. But you'll see here in a minute why we usually, when we do Newton's divided difference, we write the polynomial in a slightly different form. All right. So what I'm going to do is I'm trying to go ahead and determine what is the polynomial that goes between these points here, and it's going to have this function value f of f. So I need to determine all of my b naught values in order to fit that function to it. And so here's kind of the notation of the book. I'm going to review it so it makes it pretty clear. what we're doing is each one of my b sub n values, this would be b naught or b1 or b2, okay, each time is only a function of x to the n power and then everything below it. So for example, b2 is going to be a function of x2, x1, and x0. And then the same thing when I go ahead and find out b3, it's going to be a function of x3, x2, x1, and x0. So if these are my points here, this first one I could call x0, x1, x2, and x3. And in order to find my value of b1, I'm just going to be using those first 2 points. To find b2, I'll do the next 3 points. Now the function, in the end, I need all of my b's to get this entire function that goes ahead and fits through here. So here's the notation the book uses. This is b sub n is some function of all of those. And so what is that function? Well, for example, if I just got 2 points, okay, f of, say, 0 and 1, it's just my function values divided by x. This is just my linear term, like sort of a linear interpolation term. Now, if I want to go ahead and look at the next value of b up, all right, now I've got f of x, I, j, and k. And so then what I've got is a divided difference. This is where the term divided difference comes from, of these 2 functions. And these 2 functions here are these functions here. So I'm going to put that in there for I and j, and then I'm going to do a similar thing over here. I'm sorry, that should be k right over there. And then I'm going to do my difference of I over k. And so this ends up being sort of recursive, because now if I go up to b3, I'm going to be using this function value, which is divided differences of all of those points. Okay. So this is usually best to kind of go through an example so you can see the implementation of it. So there's an example in the textbook, and I'll go ahead and do another example here. So here's what we're going to do. We want to estimate this function sine x cosine 2x at x equals 1 using these 3 points. Okay. Now, of course, we don't normally have our function. We would just have those values of what f of x is. So if you go and determine what f of x is at 0, 0.6, and 1.3. I'm going to use this function because then we can determine the exact amount of error that we have. But effectively, we've got these 3 points at those 3x values. And so the first thing we're going to do is we're going to find b0. And it turns out b0 is equal to 0. And the reason for that is, well, what I'm doing is I'm just going to go ahead and set x to x0. And if I do that, that term's going to be 0 and that term's going to be 0. And I just have f of x is equal to b naught. And this function, sine x cosine 2x at x equals 0 is 0. So b0 is pretty simple. Now let's just go ahead and find out what our b1 parameter is. And our b1, remember, is the function value at x1 minus the function value at x0 over x1 minus x0, right? And so we go ahead and find out what those points are. And if I do that, that's 0.2046 minus 0 over 0.6 minus 0. So I evaluated the function at 0.6 and 0.6 and 0. That becomes 0.341. So there's my value of b1. And now what we're going to do is we're going to go ahead and find our value of b2. And b2, the divided difference is, remember, I'm doing those functions of a lower order over the whole thing here, which would be 1.3 minus 0. And this function right over here is what goes into there. So I need to evaluate this at 2 and 1 as well. So I need f of x2 minus f of x1. So this is not a b value, but I'm going to need to put it into the divided difference of b2. And so that right over there is all going to be over x2 minus x1. And so this will be 0.82566 minus 0.2046. And now this is going to be over 1.3 minus 0.6 to give me what that is, which is minus 1.472. All right, so now these are the 2 values I'm going to be putting into here to go ahead and find out what my value of b2 is. And if I stick those in there, this becomes minus 1.394. So now I have my b2 value. And so now I can go ahead and since this is the highest order we've got b0, b1, and b2, and we have 3 points, I can now go ahead and estimate what my function is, for example, at 1. So the function at f1 is, well, it's b0, which is going to be 0. And then I have my b1 value, so 0.341, and then I multiply that by 1 minus 0, my x minus x0. And now I've got my b2 term, so I'm going to go ahead and add a minus 1.394. All right, and that's going to be multiplied by 1 minus 0 and 1 minus 0.6 to go ahead and get what my function is. And so this Newton's divided difference goes ahead and gives me an estimate that the value would be 0.2166 at x is equal to 1. All right, so that's how we go ahead and implement this. Let's go ahead and look at approximating the error. And so here I have my points at 0, 0.6, and 1.3. Now here's the one I wanted to find. This is the true value that I'm showing. We estimated that it was around minus 0.2. And so we have an idea of what our error is. It's about, we're off by about 0.1. But let's see how we can estimate it, because normally you don't know this value. So we're not given what the function is. We're just given a table of values. So let's go ahead and determine how we could do this. And what you could do to estimate the error is to take another point somewhere, maybe one to the left, one to the right, or even something in the middle, and go ahead and create a higher order polynomial. So for example, let's go ahead and say we knew the value also at 0.8, which is about 0. So what we're going to do now is we're going to go ahead and fit a curve through there, and we're going to use the difference between our estimate and what that curve predicts to go ahead and give ourselves an estimate of what the error is. Okay? So which means now I need to go ahead and get effectively a B3 value. And so the first thing we're going to do is do a couple more divided differences. We're going to need to do f of x3 minus f of x2 over x3 minus x2. And so my x2 value, or my x3 value is 0.8, x3 here. This is x2. And no, these don't have to be in any particular order. You can do 1 and 0 and 3 and 4, anywhere you want on them. So we're just adding this point here. And so that's going to give me a value of minus 1.609. And now we're going to need to find a new, remember, a new, like similar to like a B2 value. It's not actually a B2, but it's the next order up of divided difference. And it's going to be this, minus 0.8 over 0.6, because we're using 3 and 2 there. And this value would be 1.609 and minus 1.472. And so it's going to give me minus 0.685. All right, so now this was the lowest order, the next order up. So now I can go ahead and calculate B3, which is going to be my two divided differences. So minus 0.685 minus 1.394, and all of that over 0.8 minus 0. Right there is my x3 value. And so that is going to be 0.88625. Right? All right, so now I've got a high order polynomial, and I'm going to evaluate that value at 1 to go and give an idea of what my error is. So I've got those terms that I had on the previous slide up through B2, and I'm going to add my B3 value. So I'm going to add 0.88625. And now I've got x minus x0, x minus x1, x minus x2. Right? So we've got 1 minus 0, 1 minus 0.6, and then 1 minus 1.3. And so we're going to go ahead and find out what this value is, and this is minus 0.1, which is about what my error was. We were off by about minus 0.1. So this is a way to go ahead and approximate the error that you have. And I should mention, this is just an approximation, because you never know truly what that value is of the function. I just gave it to you here so we could know exactly what it was and see how well our estimate did. All right, so let's talk about another method we can use. And what we just saw there is that's kind of tedious. If you recursively program it, you can do it somewhat efficiently, but it requires a lot of calculations. There's just another way, just an alternative way to do it. It's very similar, called Lagrange polynomials. What we're going to do, this is the function we're going to use to interpolate between our points. Okay, instead of b0 and b1, b2, we're going to do this, where we've got a summation of some functions we're calling L, those are Lagrange polynomials, times the function value at each point, and then we're going to sum all of those up. And what are those L functions? Well, those L functions are this big capital pi means the product. And so what I'm doing now is I've got a series of terms that I'm multiplying by each other, so it's going to be things like that, where my counter here is going from 0 to n, for whatever order my polynomial is, but I'm skipping one value in the middle. So, for example, if I had a fourth order polynomial, my numbers would be 0, 1, 2, and 3. And so what I might end up doing is skipping that value in one product, that one in the next one, and that one in the next product. And so which one do I skip? Well, it's the order of the polynomial I'm trying to determine, that L sub I value. Okay? So go ahead and at the typo, you can ignore that little function right there. And so let's go ahead and just implement this now. So what I'm going to have to do is let's go ahead and determine each one of these for the previous example that we had. So for example, what we're going to do is we're going to be finding, say, a second order Lagrange polynomial, so we'll call it f of 2 at point 1, so similar to the example we had before. And what that's going to be equal to, if we look at our summation here, we're going to have a function L0 times f of x0 plus an L1 times f of x1 plus an L2 times an f of x2. Okay? So that's what my function is going to be done. And now I need to determine what are my L values, L0, L1, and L2. So let's go ahead and find L0. So what is L0? So that means if I come back up here and look at my equation for L, so I is equal to 0 here. So what I'm going to end up doing is J is never going to be equal to 0. So that means on the numerator of this, what I'm going to have is x minus x1. If I skip the 0, and x minus x2. And then in the denominator, I do have that. X sub I is x0. So x0 minus x1 and x0 minus x2. So that's what my function L0 is. Let's do it L1 just to kind of show exactly how we do it. So now what we're doing is we're doing our product. We're going to do 0, skip 1, and go to 2. So what we're going to have now is x minus x0 and x minus x2. And that's going to be all over x1 minus x0 and x1 minus x2. Right? And so we could go ahead and determine what L3 is. And now in that product, we would just be skipping 0.3. Okay? So effectively, if we come over and look at this figure over here on the right-hand side, what you're doing is you're taking these three functions that are these L values, like L0, L1, and L2. And those are those light blue lines. And then I'm adding all three of them together. And one of the nice things about the Lagrange polynomial is that these functions, effectively, that we're fitting through, we're just fitting, in this case, second order polynomials, is that they equal to 0 at the other 2 points. And then, for example, they're going to have the function value at that point. So this would be the L1 if this was the x1 point. So it looks like I mislabeled this. This would be L1 over here because it's going to have the function value at the x point and zeros at the other 2. All right. Next thing I just want to mention is inverse interpolation, and let me explain when this comes up. And so you might remember from a while back I described one of the modeling works that I've done is looking at volcanic ash dispersion as a function of time. It's a fairly large computational model. And so what this model involves is there's a volcano that erupts, and we want to see how the ash disperses and diffuses in time. So if I was to kind of think of this as my time scale, I might go ahead and have initially a cloud that's got, maybe that. And then each one of these particles is diffusing and dispersing, even blown by the wind. And so at a time later, it's a little bit larger. And at a time later, it's a little bit larger. And the model takes these fairly large time steps, moves each individual particle, and then we can go ahead and compute what the area is by just finding out how many different pixel values are covered by ash. And so, for example, maybe at this point it was 131 square miles, and this time it was 436 square miles, and then it was 1,154 square miles at these particular times. And so we might say, hey, at what time did it have an area of 800? Right? What would be the time there? Because we had this value in this. So effectively, this is f of t, or we can think of it as f of x, where time is the independent variable. And what I'm trying to do now is find the value of f at find the value of x when I have a particular value of x. So this is the inverse to what we were doing before. Okay? And this often arises, but you realize it's fairly difficult to go ahead and do and implement. If I was just go ahead and take the reciprocal of all of my points, you end up with something that's fairly nonlinear. So let's look at another way to do this. And the way that we're going to do it, okay, is remember here's my function, and maybe I go ahead and fit my Lagrange polynomials. And maybe I want to go ahead and find out what's the x value when f is equal to 0. Okay? So what am I doing effectively? Well, what I'm doing, I'm going to erase that, sorry, is I've got this function that I went ahead and fit to it. So for example, I've got here I've got it in the case of a Newton polynomial. And I want to go ahead and find out when that has some particular value f. And so what I'm going to do, the way you're going to implement it, is first we're going to go ahead and determine what our function is in a more standard polynomial form of a0, a1, a2. So we're going to multiply out all those terms. And you can do the same thing with the Lagrange polynomial. And what you have are the values of A1. And so here I have it for a second order, A0, A1, and A2. These are just out of the book. But I've got effectively what my values of A0 are. So you realize they're all functions of the B's and then the values that I have of X that I have on the independent axis. And then I'm just going to go ahead and set that to what I want it to be. So for example, if I set it equal to 0 in the example I just had here, now I'm just trying to find out what's the value of X. This is root finding. And we've seen this before. We know how to go ahead and find the root of an equation. If I come back up to my area where I wasn't trying to find a 0, find an 800, I would just go ahead and take what my function value of X, subtract 800, and set that right there equal to 0, and to go ahead and find the root. So there's kind of two steps in here. You go ahead and find out what your function polynomial is. It's interpolating it, and then go ahead and set it equal to 0 and find the root. One last technique I want to talk about is spline interpolation, and you run into this a lot. This is just the third method for interpolation after Newton and Lagrange. And so first of all, let me just mention what a spline is. A spline is, here they're showing a wood joint. It's this really thin piece of wood right here. So this would be a spline joint where you put these little small pieces of wood in there to go ahead and join this corner. The reason it's called spline interpolation is to take one of those thin pieces of wood, and so for example, go ahead and put some pins down. These might be the data points that I know, and then go ahead and span this wood. This right here I might think is a good approximation of what my function looks like. So that's why it's called spline interpolation. Okay? And so if I go ahead and look at this equation here, what I'm doing now is I'm saying, oh, I've got some sort of piece of wood, and I'm sticking it through some points there, and that's what's going to go ahead and approximate my function. And normally what happens is you have a lot more data points than that, and so what I'm going to do is I'm going to fit a piece of wood to maybe those 3 points, and then I'm going to go ahead and fit a piece of wood to the next 3 points, and to the next 3 points, and to the next 3 points, like that. And so this is a little bit more common. This is different than Gauss, where we were going and doing the entire fit at once. We're going to go ahead and put different various pieces in there. Okay, so let's look at how we do that. So what we're going to do is we're going to pick an order of the function. Here I have a third order function, f. So I'm going to go ahead and fit a third order function between, for example, 3 points that I have. And the book's notation it uses for splines is A, B, C, and D instead of A naughts and B naughts. So I'll stick with that as well. But what I'm doing is I'm just fitting a function through, for example, that window there, and then that one, and that one, and that one. And what we're going to end up with is a fairly large matrix equation that we need to solve. So let's go ahead and first look at the lowest order spline. Well, the linear spline is the lowest, but that's just linear interpolation. Let's look at a quadratic spline. And so what I'm doing here, if these were my points, is that what I'm doing is I'm fitting a quadratic function between each pair of points like that. So I'm going to go ahead and have in here a function that's going to be ax squared plus bx plus c. And then I'm going to have a different quadratic that fits between those points. So let's call this a1, b1, and c1, because this is going to be a2 x squared plus b2 x plus c2. And then another quadratic through there, which would be a3 x squared plus b3x plus c3. All right? And so as I add more and more points, I'm just going to go ahead and have more and more functions. And so look at what I need to solve here. For example, just these 4 points, I've got 9 unknowns. So we have 9 unknowns that we would need to do to go ahead and fit this spline. How do we do it? Well, what we go ahead and do is we're first going to go ahead and we have to get 9 specifications. So we're going to go ahead and specify what our function value is at the 2 endpoints. So we're going to say, we know what our function value is at 0. We might know what it is at point 1. And then the other thing we're going to do is we're going to go ahead and say the derivative, okay, at each one of these points is the same. So that would be saying, for example, d of f1 dx is equal to d of f2 dx at each point. Okay, and that's going to go ahead and give me enough equations to go ahead and solve for what my 9 unknowns are. And so what I'm going to end up with is, and I have 9 here because I have these 4 points, is I have this big matrix of values. This would be A1, B1, C1, A2, B2, C2, etc. And then I'm going to have all of these values in here. This turns out to be a banded matrix to go ahead and solve for what those values are. And I solve for all of them at once. So now we're going to go use, again, LU decomposition or Gauss-Seidel method to go ahead and solve for what all of my values of A are. This works okay until you tend up to have like maybe hundreds of points, where you realize if you had hundreds of points you end up having a spline that's going to be several hundred elements long in terms of the size of the matrix. And this is just for a quadratic spline. If I was to now go up to a cubic spline, now between any 2 points that I have, I've now got 4 unknowns, A, B, C, and D. So for every segment that I need to have, the number of points minus 1, I multiply that by 4, the number of unknowns that I need to solve for. And you can commonly imagine this becomes incredibly tedious math, particularly with a large points. The end of the book kind of shows there's this alternative method for solving cubic spline interpolations. It involves taking the derivatives of these functions. Let me just mention here quickly, you don't worry about the details of these equations. They're given in the textbook. But effectively what you do is you have these two simultaneous equations where the two unknowns are these two second-order derivative terms that I have right there. And so you can solve these two equations for those two unknowns. And now what you're doing is just for each segment, you're actually able to go ahead and determine what the spline is in between them. So now if I had hundreds of points that I wanted to go ahead and do a spline interpolation from, I'd first find out what segment I want to do it, and then I would just go ahead and fit the spline through those 2 points right there, solving these two simultaneous equations here. And so there's a good example in the textbook that shows to go ahead and how to implement this. But the practical thing you should take from this is now I'm not solving a spline that goes through all of my data points. I'm just solving for a little small spline, that little small piece of wood that's going to go through a few points right there. And this works well for the cubic spline, which is a pretty good approximation. Let me just mention one last thing, which is probably fairly obvious. You can obviously do this in higher dimensions. And so here what we've got is a function that's a function of x and y. And so if I was to go ahead and do interpolation here, most of my methods could be very similar. If we look at like a linear interpolation, what you'd be doing is think of it as just taking a rigid plate and setting it between the 4 points right there. And then what I'm going to go ahead and do is just do a linear interpolation along the top line, a linear interpolation at the bottom line, and then I'm going to go ahead and linear interpolate between those two lines to get my linear value there. This is called a bilinear interpolation. The linear interpolation, because it's in two different directions that I have. And so you can go ahead and end up with similar equations for trilinear or any number of higher order multidimensional interpolations that you want to do. And that's as much we're gonna mention here. We're not going to do anything of higher order further. So let's go ahead and review what we looked at. This is sort of a long video. So first of all, we just saw that interpolation is estimating a function value based on values that you know nearby. Most interpolation generates a curve, which is going to be some low order polynomial, second or third order, between the known points that you have. We looked at Newton's divided difference. It's fairly accurate, but requires a recursive programming to be implemented very efficiently. We also looked at Lagrange polynomial. It's similarly accurate to Newton. It's a little easier to implement numerically. Then we looked at last with the spline interpolation. It turns out to be the most accurate, but it does require a matrix solution, which can be fairly large if you have lots and lots of data points. And then last thing we kind of looked at was this cubic spline. It has a non-matrix solution where you only have to look at a couple different points. You're fitting a small spline in there, and it's more efficient when you have really, really large data sets.